All right, this video is going to look at some applications using our exponential function. And the one we're going to start off with is how can we calculate our compound interest? So for example, if you put money into the bank and we leave it in there over time, how much interest is it going to earn based on how often the interest is compounded? So here's the formula that we're going to use. A equals P times 1 plus R over N raised to the NT. A is going to be the amount of money that is in the account in T years. Now keep in mind here, T has to be in years. P is equal to principal. R is the annual interest rate, okay? And N is equal to the number of times that you're compounded a year. So how often are you going to compound the interest each year? Is it just going to be once a year, twice a year, 4 times a year? And then T, and I really want to stress this, is equal to the time. How long are we looking at? Are we looking at a year, 2 years, 10 years, 50 years? Or maybe we're just looking at 1 month or 8 months or 6 months. But when we use time, T here has to be in terms of years. So for example, if we're only looking at the amount of time as 6 months, then we wouldn't plug 6 in for T because that would look like 6 years. We would have to use 6 over 12. So instead of 6 months, it would be 1/2. So T would be equal to 1/2. That's what I mean when T has to be in terms of years. So let's look at an example how we can apply this formula. We're given P is equal to $1,000, so that's our principal. We're going to invest $1,000. The rate is 6%, and we're looking at this for a time of 40 years. Determine the balance A, okay, A is going to be the amount of money we're left with. So determine the balance A compounded N times a year. So we have annually, if N is equal to 1. So that means we're going to compound the interest once a year. And so that means we're going to do that 40 times. So once each year for a total of 40 years. So if we use the formula up here, we have, again, A equals the principal, which is $1,000. And then we have 1 plus R. Okay, the rate is 6%. And remember, percent means per 100. So if it's 6%, that means 6 divided by 100, then it's going to be 0.06. So when we think of this, we're looking at 6% or 0.06. So we want to use the decimal form, which is 0.06. Okay. And then we have this raised, or I'm sorry, this is 0.06 divided by n. So this would be 0.06 over n. Well, n is equal to 1, so we can kind of ignore that in this case, but it's 0.06 over 1. And then that's raised to the power of n times t, so that would be 1 times the amount of time, which is 40 years. And that's it. So then we need to plug this into the calculator. And this is where you need to be careful with your parentheses so that you get the correct answer. So if we put this into the calculator, we'll go here and we'll type in 1,000, and then that's going to be multiplied by 1 plus 0.06, and I'm going to go ahead and type this as divided by 1, okay? Close the parentheses, and then want to raise that. There's your exponent, and you probably want to make sure you put parentheses here to be safe, depending on your calculator. And then we would have 1 times 40. And then we close the parentheses. So if you want to make sure that this 1 times 40 is all in the exponent. And then we would hit enter, and we get 10,285 point, and we'll say 72 since we're talking about money. We'll round it to the nearest cent. So therefore, the answer is 10,285.72. So that tells us that if we were to take $1,000 and we invest the money at a 6% rate, and if we leave it in the bank or the account for 40 years, then at the end of 40 years, that $1,000 will have grown to $10,285.72. And that's where the interest is compounded every year. So that means after the first year, we would calculate the interest. And then after the second year, you would calculate the interest on not only the $1,000, but the interest that you earned from that previous year. And then you would continue that process for 40 years. All right, so now we have the same problem, but we want to look at what happens if we compound the interest quarterly. In other words, 4 times a year. So if we do that quarterly, then we would have A equals 1,000, and it's still going to be 1 plus 0.06, but now it's going to be divided by 4 because it's 4 times a year, and then the exponent would simply be 4 times 40. So if we go to the calculator, we can enter this in. Now there's a neat little thing we can use with the calculator so we don't have to type all this in. Sometimes it will be helpful if you hit second function and then enter, and above that it says entry, and that will bring down the last line that you entered. So we can actually use the cursor now and we can go back and we want to change the 1 that we entered. We can change the 1 to a 4, and then if we go to the exponent we want to change this 1 also to a 4. And then if we hit enter, we get 10,828.46. So that's the amount of money we would have again after 40 years. So in this case, it's 10,828.46. So here we can kind of compare the difference. So you can tell that we're going to gain a little bit more money from compounding it 4 times a year because we're calculating that interest more times. All right, now we have daily. What if we compound the interest daily? So that means every day we're going to compound the interest. So that means 365. So once again, we could go in and have A equals 1,000 times 1 plus 0.06 divided by 365. And then their exponent would be 365 multiplied by 40. And again, you could go to the calculator. If you put this in, you should end up with $11,021. And once again, you can see because we're compounding it more often, again, this amount is going to increase a little bit more. Now, we might think of this, what happens if we continue to increase this, more times? What if instead of 365 times, what if we looked at it, say, hourly? Or what if we calculated the interest every minute? Or if we calculated the interest, let's say, even every second? So here, what we could think of is, what if we calculate this interest continuously? So if we calculate this continuously, we're going to use a different formula. So if we're looking at this compounded continuously, then we're going to use this formula here, A equals PE to the RT. Okay, and here A is still the amount, P is still the principal, R is still the rate, T is still the time. It's just now we're using this natural base E. Okay, and at the end of this video, I'll go a little bit more detail about how this works with this natural base E. And remember, the reason we call this a natural base E, one reason is because this is a unit or a constant term that is shown up kind of naturally with real life problems that we'll work out. And we can see that as we go through some of the other examples here. So if we look at compounding this interest continuously, we no longer are going to be using this 1 plus r over n to the nt formula. We're going to be using this A equals PE raised to the RT. So if we do that, then the amount is going to be equal to the principal, which is still $1,000 that we're putting in. And then we have times E. The rate is still 6%, so that would be 0.06. And that's multiplied by the time of 40 years. So if we enter this into the calculator, we would type in 1,000. And I'm going to hit second function, and down here at the left we get this e to the x, so that's a 1,000 times e raised to the, and again you probably want to, depend on the calculator, make sure you put parentheses here, 0.06 times the 40 years and close your parentheses. and we get 11,023 and 18 cents. So this is equal to $11,023 and 18 cents. Now, you may have thought this number to be a lot bigger, but if we compare this to the previous answer, notice it's a little bit bigger, but it's not a lot bigger than the daily calculation of 11,021. Here we get 11,023, so we're only looking at a couple more dollars basically. And that's going to kind of lead into we're approaching kind of a limit here with this compounding as we go to this continuous. And that's why we're using this constant term E. And once again, I'll show you a demonstration of this at the end of the video. All right, so if we notice here, the more that we compound the interest, obviously the more that you're going to have with the calculations of the amount of money you have at the end of the year. All right, so here's another example. You see this sometimes in some science classes. If you're looking at the radioactive decay, and we want to determine how long does it take for this radioactive material to disappear, or does it really ever disappear? It says here we want to let Q represent a mass of carbon-14, okay, in grams, whose half-life is 5,715 years. The quantity of carbon-14 present after T years is given by this equation. Q equals 10 times 1/2 raised to the T divided by 5,715. Now let's go back to this problem here. It says that we basically have this mass of carbon, okay, and it says whose half-life is 5,715 years. What does that mean if it's half-life? Well, first of all, the half-life means that whatever the amount of carbon you have, it's going to take 5,715 years for half of that to disappear, okay? Then here it says the quantity of carbon-14 present after T number of years. So here it says, first of all, determine the initial quantity of carbon. Well, if that's looking at the initial quantity, then that means T is certainly equal to 0. So if we're going to look at here, the quantity would be 10 times 1/2. And I'll go ahead and write this in. This would be raised to the 0 divided by 5,715. And really, if you take 0 divided by a number, this is just going to be 1/2 to the 0 power, right? And if you put this in the calculator, 1/2 raised to the 0 power, or any number raised to the 0 power, is going to be 1. So you're going to get 10 times 1. So the answer is going to be 10 grams. So 10 grams is the initial quantity that we have of this material. Okay, so that's what we start with. The second part of this question says, determine the quantity that is present after 2,000 years. Now, do you expect this number to be greater than 5 or less than 5? Okay, think about that. If we're looking at this after 2,000 years, we started with 10 grams. Do you think we're going to have more than 5 grams or less than 5 grams? All right, let's work this out and see what we come up with. Well, if we plug this into the equation, we would have 10 times 1/2, and we have T is 2,000, so that's 2,000 divided by the 5,715, okay? And if we plug this into the calculator, okay, let's see, if we plug this in, we would have 10 times, let's see, 1/2, and we're going to raise this to the 2,000 divided by 5,715 and close the parentheses. And if we hit enter, we get 7.8, and we'll say 7.85. Now, did you guess correctly? Did you say that this was going to be more than 5? 7.85 grams. So if you notice here, after 2,000 years, half of this material is still there. I mean, over half is still there. We still have 7.85 grams. Now, I'm hoping that you were able to guess less than, or more than 5 rather, because what did we state up here in the initial problem? Well, we said that this carbon-14 has a half-life of 5,715 years. So that means it's only going to be after 5,715 years that we would have 5 grams. So we're looking at only 2,000 years. So therefore, the 2,000 years, we're going to have more than 5 grams left. In this case, we're going to have 7.85 grams. All right, then we have sketch the graph of this function over the interval from 0 to 10,000. So we have our function. Okay, our function up here was 10 1/2 raised to the t over 5,715. And let's see, I can rewrite that here. Q is equal to 1/2 raised to the power of t divided by 5,715. So we want to look at the graph of this function. So if we go to the calculator, we can go to y equals, and we're going to type in 10 multiplied by 1/2, and that's going to be raised to the power of t. So in that case, I'm just going to use the variable x here, divided by the 5715, close the parentheses, and I'm going to go to zoom standard. And again, for whatever reason, I like to go to zoom standard. And we can see part of the graph here at the top, and we realize that this graph is way off. And if we think about this, it says sketch the graph over the interval from t is 0 to 10,000. Well, t is representing our x, so that means if we go to the window, we want our x minimum to be 0, and we want the x max to be 10,000. Now, what do we have to make our y value? Well, most likely a negative value is not going to make any sense here if we're looking at the amount of carbon that's available, so I'm going to just make that 0. And our y max, well, let's think about this problem. What do you think we're going to let the maximum y value be? Well, if you go back here to the first question we had, determine the initial quantity at time 0. We said the initial quantity here was 10 grams, so that's going to be the largest it will be. So that means our y max then would simply be 10. So if we look at the graph, let's see what we get. So here's our graph. It started here at 10 grams, and then it slowly decreased. And you can see that the further this line goes down over time, it even decreases at a slower rate. So if we copy this, here's our graph. And once again here, we said that we started here at 0 and we went to 10,000 years. So if you look, even here after 10,000 years, if we still have not reached 0. If we were to look here at this point, what is this, 1.2? So it's just a little bit more than 2 or so here. And if I was to plug that into the calculator, if we went to second and trace, that's where we want to calculate a value, which is 1. So when x is equal to 10,000, notice at 10,000 we still get 2.97 grams. So here, this is still at 2.97. So almost 10,000 years after this 10 grams, we still almost have 3 grams left. So you can see that it takes a very long time for this to disappear. And looking at this graph, it's going to really slow down because this graph is slowing down the further it goes out. All right, now I want to look at one more example here dealing with depreciation. And we can all relate to this if you've ever purchased a car or any type of equipment. And it says here that after T years, the value of a wheelchair conversion van that originally cost $49,810 depreciates so that each year it is worth 7/8 of its value the previous year. So from this, we want to find a model for the value with time, so V of T, the value of the van after T years. So we're looking for the equation here. Well, we know the original value is 49,810. Now, if we kind of think of this to our example above here with the carbon, if you notice in the equation here, equation was talking about the half-life, and notice up here we had half here, okay, and this is the amount we started with is the 10. So let's see if we can kind of use that same idea down here. Well, the original amount is $49,810, and then instead of the half-life, it says that it's worth 7/8 of its value the previous year. So here we're going to use 7/8, okay, and then that's going to be raised to the number of years. So that's going to be the formula to represent the value of the van. And of course, if we plug 0 in, we would get 7/8 to the 0, which is 1, and 1 times our amount, we would have the $49,810. Now, we want to use this formula to determine the value of the van 4 years after it was purchased. Well, if we want to calculate the value 4 years later, then we would simply plug 4 in for t, and we would have 49,810 multiplied by 7/8 raised to the fourth power. Okay, and to save a little bit of time, if you enter this to the calculator, you should end up with somewhere approximately $29,197.71. So after 4 years, you can tell that the value of this van has really depreciated over time. All right, I wanted to finish up with one last thing here. We started out looking at the formula for interest, and let me write down that formula here again. We had A equals P times 1 plus R over N raised to the NT power. Now, if we were to ignore, if I rewrite this, and if we were to ignore the principal, for example, if we think of the principal as being equal to 1, and if we then would have 1 plus our rate, leave that as 1, and then we have over n raised to the n times the time, we could make that also 1, okay? So basically, if we ignore the time, the principal, the rate, and we just look at n, which is the number of times that this money's compounded, and if we were to plug this in over here, you can see the computation. All we're changing here is the value of n, basically. Okay, so we're having 1 plus 1 over n raised to the nth power. So 1 plus 1 over 1 to the first power. If we look at this yearly, we get an answer of 2. Well, then semi-annually, we get 1 plus 1 over 2 squared. We get 2.25. And then quarterly. And notice what's happening to this number. It's starting to increase, but it's starting to increase at a slower rate as we go from quarterly, monthly, weekly. So that's weekly would be 52. Daily is 365. Hourly, well, you take 365 times 24 and you get 8,760. And notice what's happening here from daily to hourly. Notice we're getting this 2.714, 2.718. And if we go to every minute, we get 2.7182. And then every second is 2.71828. And what number does this look like? Notice this number here, this decimal seems to be approaching a number, and we talked about this, and this is approximately then equal to our natural base E. Okay, so that just kind of shows you a little bit of a connection here of where this natural base E is coming from. As we go through these calculations, we can see that it is approaching this decimal, kind of like the same idea as when we talked about the Greek letter pi representing 3.14. Here, our natural base E is approximately this 2.718.